Hey everyone, so welcome to our review of what happened in section 1.3.1. The main concept of this day was looking at finite differences and seeing if we could find a pattern for different polynomial functions. So the first one that we looked at was the quadratic function, and we asked ourselves, okay, if we take the finite differences of all the y values, what kind of function will those make? So we first started out by looking at what is a finite difference. So finite differences are basically the change in y. So that's why it's notated with this delta y. So the phrase delta y, change in y, or finite differences all mean the same thing. And all they're asking you is when you start with the y value, for example 9, and you want to go to the next y value, how much do they change by? And you notice here, 9 minus 5 gives us 4, so that makes negative 5 our finite difference. Okay, so we looked at all of these finite differences here once we calculated them, or once they were calculated, and said, well, what's the change or what's the pattern in them? And if you look, you can kind of tell, and you guys can see that we know that the change in the y values, actually the delta y's, change by adding 2 every time. So for every delta y, the pattern is adding 2. So there's a constant change in the delta y's, which is really interesting and is going to become a common feature of quadratic functions that we notice. And we'll kind of talk about that in a bit. The other thing to notice about finite differences is that the larger the finite difference, so for example 5 as compared to something smaller like 1, if you look at the function part of it that covers, this part of the function is steeper than this part of the function. So the larger the finite difference, the steeper the function is. Okay, so then the other one that we looked at a couple more quadratic functions, and what it ended up showing us was that if you have a quadratic function, the finite differences will make a linear function. So let me show you the first one, and we'll go off of that. Okay, so our first quadratic function that we investigated was y equals 2x squared minus 3x plus 1. We made a table for it, looked at the values. Another thing to notice is that we're making tables horizontally right now so that we can kind of mimic what's happening on the x-axis. So let's say I looked at 2x squared minus 3x plus 1. We speculated that because it has a constant change, you think to yourself, what's that function that has a constant change? And that is going to end up being the linear function. So let's prove that. So if you do the table for this 2x squared minus 3x plus 1, okay, here's what you end up getting. So for negative 2, the function maps to 15. For excuse me, for negative 1, it goes to 6. For 0, it goes to 1. For 1, it goes to 0. And for 2, it goes to 3. So let's calculate our finite differences. Remember, all you have to do is every time you look at how the y changes. So to go from 15 to 6, that's a minus 9, so our delta y in that case is minus 9. 6 to go to 1 is minus 5. 1 to go to 0 is minus 1. 0 to go to 3 is plus 3. So the same way that we did before, you look for the change in the finite differences, and in this case, we notice it's got a constant change of adding 4 every time. So what does this mean? So what we're looking at then is maybe graphing the finite differences and seeing what kind of function they make. So we ended up graphing it, and let's see if I can do this pretty accurately. What we ended up seeing was, yeah, it does make a linear function, so let's graph it. My graph isn't large enough for me to be able to do a negative 9, so we're going to go to the first one we can do. So if you graph x value negative 1, y value negative 5, so over 1, down 5, so this is the first finite difference I can graph, right? Let's try the next one. So the next one we see on here is 0 and 1, negative 1. And we did this in class, so you guys should have this in your notes. And then the next finite difference we graphed was 1. Oops. Sorry, guys. Was 1 and positive 3. So then we go over here and go to 1 and positive 3. And if you take a look at these things, you'll notice, voila, makes a straight line, aka a linear function. And interestingly enough, if you guys look at the equation of this function, or you look really closely at this function, you notice from one point to the next, it rises 4 and runs 1. So that means that this number here, this finite difference that we found, is actually the slope of the line. So the m is equal to whatever that finite difference is. Pretty cool. So you guys can make the assumption then, we can say, okay, if I ever get a quadratic function, we did a couple of these in class, we can make the connection that the finite differences from this quadratic, when you graph all of the delta y's, you're going to end up getting a linear function. So we concluded then, for our notes, after doing some investigations around some other functions, you all noticed a couple of different things, and this is what we had in the notes. So we investigated the constant function. That's any function where all the y values are the same. And we found out that when you look at the constant function, the finite differences give you a all of the finite differences end up being 0. All 0. And that's the case for any constant function. Then we went on to do the linear function and asked ourselves, okay, well now we take a straight line. What's going to happen to all those finite differences when we graph them? And all the finite differences end up being the same. So inevitably, the finite differences of linear functions, a constant function. We just discovered this one. We found out that when we do a quadratic function, and that was the work that we just did. Okay, when we do those, finite differences are linear, so it makes a straight line. And finally, after some experimentation and some of the examples that we did, we discovered that the cubic function, and actually one of the things that we had a couple of you were doing, we took the differences of the differences, and in that problem, let's see which one that was. I think it was 99. Let me make sure. Yeah, in 1-99, if you guys tried a couple of the cubic functions, the conclusion from that one were a couple different things. We saw a lot of neat patterns, so if you want to check in with some of the other people, you can see what that was, or what some of those that were that we noticed. But the big idea that came out of this was that cubic functions, the delta y's, are quadratic. So you can kind of draw this conclusion that every time you just drop the degree by 1 whenever you're finding the finite differences. So you can create functions for the finite differences based on the types of functions that you started with, as long as, in this case, they're all polynomials. So if I had a 4th degree polynomial, the delta y's are going to be a 3rd degree polynomial. If it's, let's say I gave you guys the original function, f of x equals x to the 20th power, we can, based on the patterns that we've noticed, this is so cool that you guys can look at this and discover these things, that the delta y's are going to make a function that looks like x to the 19th. So, kind of neat. And this is the main idea from today. There were a lot of other things that we did where we looked at patterns and we looked at taking the differences of each one. But this was the core idea from today, that if you have a constant function, the finite differences are all 0. The linear function, the delta y's, make a constant function. The quadratic function, the finite differences are linear. And for the cubic function, for any cubic function, the finite differences are quadratic. So hopefully you can check in with someone else. Or actually, I'm going to just write in the equation that we worked with, and maybe you can do this on your own. The equation from the notes that I asked you guys to work on, and this actually makes this cubic to quadratic connection very, very clear for us, but the equation from the example in the flip book, okay, I'm not going to do this right now, but the equation was, it said analyze the finite differences and this one in 1.3 of your flip book, section 1.3. Oops, maybe 4 is better. For this function, f of x equals, so it's going to be a kind of a strange function, but you know what? It works out really nicely. So if you weren't here, make sure that you take a look at it and try it out on your own. So we end up with 1/3, or we start out with 1/3 x cubed plus 1/6, or no, 1/2 x squared plus 1/6 x. So here's a cubic function, right? You do a table, make a table, analyze all the finite differences, and you'll notice a really, really nice pattern shows up and really proves to us, or kind of, not proves to us, but verifies for us that we can intuitively say that cubic functions will give us quadratics as the finite difference equation. So there's your conclusion from this day and this 1.31. That was the big idea, and the core idea was this, what we had done on the previous slide. So this guy right here. So if you don't remember anything else, this is it. Okay, so hopefully you had some other connections that you made and you remember from class, and maybe if people are absent you can share those with them, but otherwise that is it for 1.31. Thanks a lot.